Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to talk a little bit about going from inodes to file names. So how do we do that? Recall that the inode has all of the metadata. So what connects that metadata to a file name? Well, it's a directory entry. So what do these look like? If we look at the generic directory entry, it is something that maps names to the inodes, and each directory is treated as a file, which, if you know anything about Linux, should not be surprising because in Linux, everything's a file. So if we look at a directory entry, it starts out with an inode. Here's our tie-in to the inodes. And then we have a record link and a name link. And then we have the name. Now the name can be up to 255 characters. Now because of this record length being 2 bytes long is a bit wasteful. So what has been done in recent versions of the ext file system is that if you set a feature, you can have additional information in the inode. And in particular, we take part of that name length. Again, it can only be 255 bytes. And we use that extra byte that we were wasting before for a file type. So we have a file type of unknown, just a regular file, directory, character device, block device, FIFO, socket, or symlink. And these should look familiar. We've talked about these in previous videos and how this is in the mode information that is stored in some of these entries. And then we have our name string. So that's a small change. Now, another thing that you'll see in directory entries, we will install a directory tail. Now, what's this directory tail? It's a phony entry at the end of each directory block, and it adds checksums to the directories. So why is it a phony directory? We fake it out in order to have older systems that are not aware of these things not die or malfunction. So how do we do that? The first thing we do is we set the inode to 0. Because 0 is an invalid inode, legacy systems will ignore it. They'll ignore everything that comes after it. We set the record length correctly to be 12, and the name length is set to 0 because there is no name. We set the file type to a special value of DE. We then store a 4-byte checksum. So if you do the math here, there's 4 plus 4, and these three add up to 4 bytes. That's 12 bytes. Some other things that have been added. Hash directories. Why do you want these? Well, why do you hash anything? Those of us in security, of course, have reasons for hashing things. But general computer scientists will use hashes in order to improve performance. So if you have an older system and you're not using hashes for your directories, you have to do a linear search through the directories, which might take a while if you have lots of files. So here again, we fool the old systems by storing hash entries after the end of the directory block. We start an entry with a 0, and it says, oh, I must be at the end. Then we have our directory nodes in a hashed balance tree, or sometimes called an H tree. That's just shorthand for hashed B tree. And the ext4 index flag has to be set if your inode contains a directory H tree. Now, if you have hashes that are stored for your directory, you will still have their traditional dot and dot entries stored without the hashes. So these are not part of that whole system, and this is meant to speed things up. So what does a hash directory look like? You have your root hash directory block. It starts out, as we said, with your dot and your dot dot, and these are 12-byte entries. So we have our traditional 12-byte directory entries, and then we have an inode number set to 0 to fake it out. We have a hash version, and we have 6 different choices. You can see those here. We also have hash info length. We'll talk a little bit more about that, but that is traditionally set to 8. If you look at the length, how deep does this tree go? There's a flags entry, which is currently unused. There's a limit, the maximum number of entries that follow this header. There's a count for the actual number of entries. We also have the block. What is the block within the directory that corresponds to the first entry? And then we have entries. So the remainder of the block is 8-byte entries, and that matches our hash info length. So what does this look like? So that was the root directory entry. What about the interior directory entries? They also start out with the fake entry that points to inode 0, and they have a record length set equal to the block size. Traditionally 4K, the length is set to 0, and the file type is also set to 0. Then we have the limit, the max entries that follow, the count, the actual entries that follow, and the block. Again, this is the block within the directory for the lowest hash value of the block. And then we have directory entries. Now, the reason that I have these values here in red is that depending on where you look, I found these entries, and other places I did not find these entries. So I think it might depend on the exact version of the file system that you're running as to whether or not these 3 guys are present. So something to keep in mind. And then finally, the hash directory entry itself is going to be 8 bytes. So we have 4 bytes for the hash value, and then 4 bytes for the block within the directory of the next node. So this tells us where to go next if this doesn't match. Here we also have the very end, the tail. And in the end, we have a reserved 4 bytes set to 0, which will cause it to be ignored, followed by a checksum. So there you have it. That is how we map our inodes to file names. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon.